Well, hi everybody. I hope that you guys are doing okay and that you're not getting too bored yet. This is a time that I really wish that we were in school because it's the one time of the year that I actually use the Pepsi stuff in my room for educational purposes. That's why I started off this PowerPoint with the picture that you're looking at, which is a picture of the Pepsi stuff from many years ago when there was a little bit less in the collection. But we're going to talk about why I use that and how it relates to geometry as we go through the stuff today. So the topic in our next chapter, which is chapter 7, is similarity. And we're going to be looking at shapes that are similar to each other. What similar means in geometry is that things are the same shape, but not necessarily the same size. You see the symbol for similar up in the corner of this. It looks like a tilde like you might see in Spanish. You've seen that before when you've seen the congruent symbol in geometry. Congruent means things are the same size and shape, and it looks like the similar symbol with an equals under it. That similar means the same shape. The equals that goes with congruent means the same size. So again, similar, it's the same shape, but not necessarily the same size. So all of the fish in these pictures are similar. Sometimes people think that they have to be different sizes if they're similar, but as long as it's the same shape, you're good to go with similar. So if you think about that definition of similar, it should kind of make sense what the Pepsi stuff has to do with this. If you guys were out at school today, what I would probably do is have you look through the Pepsi stuff and grab different things that are or aren't similar. There are a lot of different sets of things that are similar. There's cans of different sizes, for instance. I've got one can that I got years ago in England that's a 100 milliliter can of pop. That's like 1/3 the size of the cans we get here in America. And I've got a cooler that's shaped like a can of Pepsi, but it's way bigger than all of the others. There's also bottles of different sizes, including little tiny mini bottles that people sometimes ask me if there's actually Pepsi inside them. I can tell you, yeah, there is, but it's really flat because years ago, like back when Mr. Bodie was a student at Garrigan, I actually drank one of those on a dare. But there are actually lots of different things that are the same shape, but different sizes. Something that people sometimes get goofed up on when we do that activity is that it doesn't matter what the logo on the bottle or can is, it just matters that they're the same shape. So an old bottle and a new bottle that are the same shape are going to be similar. Another thing that I'll sometimes talk about that is similar are maps and the places that they're maps of. Here, for instance, you're looking at the whole United States, but the actual country is a lot bigger than the map that you're looking at. It is, however, the same shape, but different sizes. There are two really important properties that happen whenever you have similar polygons. One of them is that in similar polygons, the corresponding angles are always congruent. So angles that match up have to be the same size. That's how you end up making the exact same shape. It's also why sometimes when we do that Pepsi activity, things aren't quite as similar as they look. You'll end up finding things where the can is shaped slightly differently, and so technically it's not similar because the angles wouldn't be 100% matching up. Also, corresponding sides have to be proportional, which means as one thing gets bigger, the other gets bigger in the same way. So the first thing that has to happen when you have similar shapes is that corresponding angles have to be congruent. In the picture on the left, you can see that all three possible pairs of angles are marked the same, and that's how I know that we have congruent angles. Since all three are the same, this is going to be similar shapes. On the right, if these were similar, I would know automatically that angle A and angle V would be the same, so are angle B and angle W, C and X, D and Y, and angle E and angle Z would also have to be congruent. The other thing that has to be true in similar shapes is the corresponding sides are proportional. And if you look at these, you can actually see that each of the sides that match up is 1.5 times as big in the second shape as it is in the first. So like if I take 10 times 1.5, I get 15, 6 times 1.5 is 9, 8 times 1.5 is 12. So everything is getting bigger by the same amount. They're being multiplied by the same thing. That's what proportional means. You can see both of those things happening in these two pairs of shapes. On the top one, if you look around quickly, you'll notice that every pair of angles that matches up is the same. And if you compare the lengths of the sides, you'll notice that the markings on the right are 10 times as much as those on the left. The same kind of thing happens, though it's harder to see in the bottom. If you look at the angles that are in the same place, they're all marked to be congruent. And if we look at the lengths of the sides, everything is twice as big on the right as it is on the left. So the corresponding angles are congruent, the corresponding sides are proportional. In this picture, all three of the triangles will end up being similar, and that's because A, all the sides are actually twice as big as C, and in B, everything's 3 times as big as C. So again, all the corresponding sides are proportional. That's what tells us that this is going to be similar. A term that'll come up when you do some of the problems over this section is the term scale factor. And all scale factor means is how much do you multiply by to get from one polygon to a similar polygon. So like there's a picture here where if you look at the corresponding sides, we go from 8 to 16, 9 to 18, and 6 to 12. Everything's multiplied by 2, so we'd say that the scale factor is 2. One of the things you'll be asked to do is to look at pairs of polygons and decide whether or not they're similar. And again, to do that, what you've got to do is think about the two things that have to happen. The corresponding angles have to be congruent, and the corresponding sides have to be proportional. If either of those things doesn't happen, then they're not similar. If they both do, then you're good to go. So here's the first of the pictures that I had on the previous slide. The first thing I'd probably do here is look at the sides of these quadrilaterals, and it's not too hard to figure out when you have things like 10 and 5, 18 and 9, that all the pairs of sides that match up, they're half as big on the right as they are on the left. What's not entirely clear right away is whether the angles also are going to end up being congruent. And what I have to do is figure out, so how big are the missing angles that we have? I did that by looking at the one on the left. I remembered that a quadrilateral has 360 degrees, and I subtracted off the angles that I knew to figure out that the one that's missing has to be 90. Well, if you look on the right-hand side, you'll see the little box that shows that's a right angle, so yeah, it's the same as the one that's over there. You could have done this with the other quadrilateral too. You would have gotten that the missing angle is 110. And so, yeah, all the angles are congruent. The sides end up being half as big on the right as they are on the left. And so, yes, these are similar. Not every pair of polygons you'll see will be similar, though. Here, if you look at these, what I did is I tried to find the missing angle from the quadrilateral on the right. And so I took 360, I subtracted off 45, 155, and 70. And I found that the missing angle has to be 90 in that one. But if I look at the corresponding angle over on the left, it says 85. Since those angles aren't congruent, these can't be similar. Now, it would also turn out that if I tried to figure out what you multiply by to match up the sides, it's not going to be the same on every possible matching side. But as long as one or the other doesn't work out, these are not similar shapes. So the other thing you're usually asked to do when you're working with similar polygons is to find how long missing sides are. Like in this problem, they tell us we've got two similar triangles and we're supposed to figure out the length of DF, the longest side of the big triangle. That's actually pretty easy to do in this problem. You could just look at two sides that you know match up, like 4 and 12, and you can figure out that to get from the small triangle to the big one, they multiplied by 3. I could have looked at the bottom instead and figured out 5 times 3 is 15. So once I know that I'm multiplying by 3, all I've got to do to get the answer is take 6 times 3, and I know that D is the correct answer. It's going to be 18 centimeters long. It's not always quite that easy though, and this picture kind of shows you a problem where you have to think a little bit more on that. We again have two similar triangles, but this time we're supposed to figure out what's x and what's y. And it's not quite as easy to figure out something you can just multiply by easily to get that. The key to doing problems like this is that corresponding sides are proportional. A proportion just means equal fractions, and so that's why I've got fractions that are equal written down to solve this problem. First time I wrote down 6 over 4 equals 7 over x. The 6 over 4 just comes from matching up the shortest side of each of the two triangles, 6 on the left and 4 on the right. 7 over x, I'm looking at the medium side on the left and the medium side on the right. And so I match up what corresponds and I come up with a proportion. You should know from algebra that all you do to solve a proportion is cross multiply. And if you look at what I did, I took 4 times 7 divided by 6. And basically the answer is 4 and 2/3, 4.6 repeating. I did basically the same thing to find y. I took 6 over 4 equals 8 over y. Again, short side over short side, and this time it equals long over long. I cross multiplied, and it turns out that y must be 5 1/3. This is actually a very similar problem, and I'm going to let you guys look at it for a minute, just with silence in the background. We'll see if you can come up with an answer, and then we'll talk about exactly what you do to do it. So they give you the stuff that matches up in these, and you can see I put 30 over 105 equals 28 over x. And again, all we're going to do is just cross multiply to come up with the answer on that. It turns out to be 98, would be 98 meters, which is D for your choice. Sometimes in pictures like this, people aren't quite sure why 30 and 105 match up. They think that maybe the 30 should go with segment RS instead of RT. But the whole idea when you have parallel lines is, remember, alternate interior angles are congruent, and so you do go to the opposite side of the second triangle. And so again, the key thing in this section and really the whole chapter we're going into is similarity. And similar, again, means things that are the same shape, but not necessarily the same size. The two key things that are important are that the corresponding angles have to be the same, and the corresponding sides have to be proportional. You'll be doing some problems with those, and of course next week there will be a quiz that deals with similarity, so you do want to make sure that you know those key ideas.